Euler Path and Euler theory. So in this video, we're going to understand what do we mean by Euler Path, Euler circuit, Euler theorem, Flory's algorithm, and we're going to solve application using Euler theorem. An Euler path is the path that covers every edge of a graph once and only once. Every edge must be traced and no edge can be retraced. So keep in mind that the path starts at one vertex and ends at another one. So let's see an example of an Euler path. So we're going to start at A and end at G, and we're going to trace every edge once and only once. Keep in mind, if we join G with A with the segment, then we're going to have an Euler circuit. So we have to add over here also A, and it will become an Euler circuit instead of a path. Another example of an Euler path starting from A and ending at G is as follows, and you can find as many as you want. So that's another example of an Euler path starting from A and ending at G. Euler theorem is a very important theorem. If a graph has exactly two odd vertices, then it has an Euler path but no Euler circuit. And keep in mind the Euler path here starts at one of the odd vertices and ends at another one. If a graph has no odd vertices, all even vertices, then it has at least one Euler circuit, and the Euler circuit must start and end at the same vertex, and it can start at any vertex. If a graph has more than two odd vertices, then it has no Euler path and no Euler circuits. If we look at this graph, let's check if it has an Euler path. The degree of vertex A here is 2. The degree of this vertex is 4, and the degree of this vertex is 4, while the degree of D is 3, and the degree of E is 3. So notice we have 2 or exactly 2 odd vertices. Then this graph has an Euler path. So we're going to start at one of them, which is E, and let's see an example of an Euler path. So this is an example of an Euler path, and we can find another one because we said it has at least one Euler path. So another example of an Euler path, we're going to start at D this time and end at T. If we look at this graph, we can tell that all vertices are even. So the degree of A is 2, while this one is 4, this one is 4, this one is 4, 4, 4, and 2. So all vertices are even. So it means this graph has at least one Euler circuit. So we're going to start at B, and we're seeing an example of an Euler circuit. If we look at this graph, does it have an Euler circuit? So we have to check the vertices. So the degree of A is 4. And the degree of B is 2, while this one is 4. The degree of D is 2, while this one is 4, and this one is 2. So all vertices are even, so it has at least one Euler circuit. So we're going to start at A again, and we're going to see an example of an Euler circuit. We can follow the numbers. If we look at Coinsberg Bridge, we represented the islands with vertices, and if I can go from one island to another with a bridge, we can draw an edge between the two vertices that represent the islands. And how about now this graph? Does it have an Euler path or an Euler circuit? Again, we have to look at the degree of the vertices. So the degree of A is 3, the degree of D is also 3, and the degree of C is 3, while the degree of B is 5. So all vertices are odd, or it has more than 2 odd vertices. So no Euler path or Euler circuit exists here. Flurry indicates that anytime you're trying to find an Euler path or circuit, you have to erase the edge. So this graph, since all vertices are even, it has at least one Euler circuit, and we're gonna use Fleury's algorithm starting from A to find one. So we're gonna start at A, and we're gonna go from A to D, then D to C, then C to F, then F to D, then D to B, then B to F, then F to E, E to C, and C to A. So that was an Euler circuit. So we can number the edges. So starting at A again, so this was the recap for the circuit, but Fleury indicates that every edge you trace, you have to make it dash or erase it.